Hi everyone, welcome back to Data Cadence. My name is Rahul and I work as a senior applied research scientist. And in this video, we are going to have a look at one of the most interesting interview questions, that is which machine learning algorithm is the best. Now it's true that there isn't a single best machine learning algorithm that usually outperforms others in all scenarios, but this question, however, is incredibly valuable in an interview setting because it evaluates a data scientist's ability to assess and choose the right tool for the job based on specific circumstances. It also tests your depth of understanding of fundamental algorithms and how we can balance trade offs like accuracy, interpretability, training time, and a lot more, depending on the problem at hand. So, in this response, I will provide you with an exhaustive answer corresponding to each factor that you won't need to refer any other resource for this particular question. I can guarantee that. And additionally, this discussion will serve as an excellent refresher for those who are looking to revisit and reinforce some of their core machine learning concepts. So this video will often be divided in two parts. In the first part, I will try to cover certain factors that will help you choose which machine learning algorithm should you pick. And in the second part, we will talk about a bit of those advanced factors. So like I mentioned, I will try to keep it as exhaustive as possible. So in part one, we will have a look at few of the basic factors that you should be aware of. And in the second part, we'll look at some of the advanced factors that will also help you decide as to which machine learning algorithm you should pick based on your particular problem. So without further ado, let's begin. So like I mentioned, there is no specific answer to which machine learning algorithm is the best. So none of them are the best. It all depends on the problem at hand and various factors. And you do have too many choices. So you have simple algorithms like KNN, logistic regression, naive bias, SVMs, decision trees, random forest, GBDTs. So all of these are more like classical machine learning algorithms, been there for quite some while, and they work typically well in a realistic setting. And then we do have deep learning architectures based on neural networks and all of that. So again, these choices are not an exhaustive list, but these are often the most common choices that you have at hand, and a lot of these will solve for the problem that you are trying to cater to. So let's talk about the factors that you should often consider when looking at each of these algorithms. So the first factor is obviously the training time. So the training time is again a very important factor. That is how much time does it take for you to train these particular algorithms based on the data that you have and produce a model. So let's start with KNN. So KNN will take a minimal training time because it doesn't learn a model during training. Instead, what it does is it stores the training data and performs all the computation at runtime. So essentially, it's no training time, and that's one of the reasons that KNN is also referred to as a lazy learner in the machine learning paradigm. Then let's talk about logistic regression and naive bias. So both have relatively short training times as they involve simple linear equations and probabilistic computations respectively. So again, the training time is very short. In SVMs, they can have longer training times, especially with large datasets due to the complexity of solving the optimization problem. When it comes to decision trees, the training time can vary depending on the depth of the tree, but generally it is efficient because people refrain from training decision trees that are too deep because then you run into problems like overfitting. But generally, the training time is reasonable in decision trees as well. When talking about random forest and GBDTs, okay, when I say GBDTs, I refer to gradient boosted decision trees, or if you also might want to call it XGBoost, that is also fine. That is one and the same thing. But these ensemble methods can have significantly longer training times as they involve training multiple trees and then combining their results at the end. And when I say multiple trees, it could be hundreds of trees, or in some cases, it could be as large as thousands of decision trees that you are trying to train for each of these methods. And in particular, random forest can still be taking lesser training time because of the fact that you can train it in parallel. But when it comes to gradient boosted decision trees, it's hard to parallelize them because there is a sequential learning that is going on. So the next model that you are training will learn from the errors made by the previous model. So there is a sequential learning. So random forest and GBDTs both will take larger training times because of multiple trees. But even if you were to pick one of them, so random forest can still be faster because you can easily parallelize the same. When it comes to neural nets, so depending on the architecture, the training time can be very long, particularly for the deep neural networks that we have. So the second factor that we have is runtime latency. And when I say runtime latency, it basically refers to the time it takes to make a prediction once the model is trained. So let's talk about different models here. So let's talk about KNN. So KNN has a high runtime latency. Why? Because it needs to compute the distance between the input and all the training samples at runtime. which can be really, very much time taking and a time consuming process. When it comes to logistic regression and naive bias, both offer very low runtime latency due to their simple mathematical operation. So these are very good algorithms if you are solving a use case which has a extremely low latency requirement as one of the primary things that you need to cater to. So in such cases, logistic regression and naive bias could be a good choice. When it comes to SVM, the latency at runtime can be moderate, especially if you're using a non-linear kernel, as the decision function that you're trying to compute may involve complex computation. So they have moderate latency, we can say that. And decision trees, when it comes to decision trees, so these are generally fast at runtime because the prediction only involves traversing the particular tree. And like we mentioned, that people refrain from training decision trees that are too deep. So these are generally fast at runtime. When it comes to random forests, so definitely they are slightly slower than a single decision tree, but still they are quite efficient. As we mentioned, that they are easy to parallelize during the training time also, but at the runtime also they have fairly well. They do fairly well when it comes to the runtime latency. When it comes to GBDTs, these are typically slower than random forest due to their sequential nature of the boosting that we discussed, but still they are reasonable and used fairly well in a lot of the industries and in a realistic setting. When it comes to neural networks, depending on the network size, again, it could have a higher latency, and particularly deeper networks can have higher runtime latency. So that is something that you need to know. The third factor that we are going to talk about is interpretability. So interpretability is the ease with which a human can understand the decisions made by your particular model. When it comes to KNN, you do have a moderate interpretability. You can explain the predictions based on the majority class of your nearest neighbor, but still it's less clear why specific neighbors were chosen in any particular scenario, right? So when it comes to logistic regression, this is usually highly interpretable, especially when using a single feature, and the relationship between the input and output is very much clear. Naive bias, when it comes to naive bias, it's fairly interpretable again, as it's based on conditional probability. So you can do some sort of interpretation based on these conditional probabilities. And when it comes to SVMs, these can be harder to interpret, particularly with the non-linear kernels, because a lot of these kernel functions, what they essentially try to do is to project your data into a higher dimension, and they are try to make a linearly separable boundary to separate the data. But long story short, especially with non-linear kernels, SVMs can be a bit hard to interpret. When it comes to decision trees, these are highly interpretable as the decisions are made based on a clear and hierarchical rules, and these are often easy to visualize. So it's nothing but a nested if-else condition that you are looking at. So decision trees are highly interpretable in that regards. Random forest have a lower interpretability than a single decision tree because obviously it's an ensemble of many decision trees. When it comes to GBDTs, the interpretability is similar to random forest, as interpretability would decrease as you keep on adding more trees into your ensemble. For neural nets, generally they are having a low interpretability, particularly for deep neural nets, where the decisions are made through a series of complex transformations. And neural nets are also referred to as black box machine learning algorithms. And when it comes to interpretability, so there are techniques like shapely values or SHAP, or algorithms like Lime that can help you do a lot of the stuff on interpretation, and all of these are model agnostic. That is independent of your model choice. You can have a really good layer of interpretation. Maybe that's the topic for another video, but these are certain generic things that you need to keep in mind when it comes to interpretability. Let's go to the fourth factor, that is scalability. So KNN's, so when I say scalability, it basically refers to the ability of an algorithm to handle large data sets efficiently. So KNN has a poor scalability, and it's obvious because you need to store and compute the distances for all the data points, and that makes it poor when it comes to scalability. Logistic regression and naive bias, again, both scale well with large data sets. When it comes to SVM, so scalability is definitely a concern if you have really large data sets, because when you're using a non-linear kernel, so the time complexity at the inference time becomes really high, and they don't typically scale well when it comes to larger data sets. When we talk about decision trees, so these are generally scalable, although large trees may become cumbersome, but that is something which people avoid. So these are generally well scalable. When it comes to random forests, so these are more scalable than SVM, say for example, as it parallelizes well, like we discussed. When it comes to GBDTs, these are less scalable than random forest due to the nature of sequential learning and boosting, but still these are manageable with the right tuning. When it comes to neural nets, so scalability is often good with the right kind of hardware, for example, GPUs and TPUs, but deep networks may require significant resources when it comes to scalability. Let's talk about the fifth factor, that is say accuracy. So in KNN, the accuracy can be very accurate if the data has a simple structure, but KNN is often sensitive to noisy data. And when I say accuracy, it basically refers to the proportion of correct predictions made by the model. When it comes to logistic regression, this is often very effective for binary classification problems where your decision boundary is having a linear surface, right? So you can have a linear decision boundary and it's very effective in those cases. When it comes to naive bias, so it works well with categorical data, but it can often struggle with correlated features. That's one of the assumptions that we make when we are, trying to derive the naive bias algorithm. But definitely, it can struggle with the correlated features. SVMs often have a high accuracy, as we saw that it comes at a trade-off between the accuracy and the runtime and the training time complexity. But SVMs are often highly accurate, particularly with complex decision boundaries, and this all happens because of the kernel trick, as we have seen. When it comes to decision trees, they can be prone to overfitting, leading to a lower accuracy. If you grow a decision tree which is too deep, so it can definitely have those problems of overfitting, but also leading to a lower accuracy. When it comes to random forests, so these are typically more accurate than a single decision tree due to the ensemble learning. So essentially, you are training multiple decision trees and then doing a majority vote or a mean or median based aggregation towards the end. So these are typically more accurate. When it comes to GBDTs, often these are highly accurate as boosting focuses on correcting the errors from the previous trees. And GBDTs or gradient boosting is one of the favorite choice of a lot of Kagglers because these often result in a highly accurate performance, and that is the reason that a lot of Kagglers prefer it for a lot of competitions. When it comes to neural nets, so these can achieve high accuracy, particularly with deep architectures, but again at the cost of increased complexity. And as you make your neural network architecture more complicated in nature, you do have chances of a potential overfitting, which could be another problem. So these were some of the very important factors that we saw in the part one. I will take a pause here and we will have the rest of the factors discussed in part two. So rest of the factors like handling high dimensionality data, robustness to outliers, ease of use and implementation, handling imbalanced data and all of that. So these are certainly a bit advanced than this. So we will cover that in part two. But I hope that this particular video gave you a lot of insights as to which algorithm is best corresponding to the situation that you have at hand. And this is often very important to understand all of these as a data scientist, because in a realistic setting, whenever you are solving a problem, you would be having a lot of these choices, but which choice to make based on your particular scenario will depend on all of these factors. And I hope that all of these factors gave you a clear understanding of what you should do, or even when you are asked in an interview, how you should answer to this particular question. So if this video particularly helped you in learning about these concepts, so definitely do press the like button and subscribe to this channel for more such content around data science interview prep and a lot of the theoretical concepts, machine learning, programming, and a lot more. So subscribe to this particular channel and stay tuned for more updates. And until then, keep learning and stay safe. See you in the next video then. Bye-bye.